Okay, we're going to talk about Chapter 4 out of Pipe Welding Procedures. This class is still pertinent to Weld 2510. It's also applicable to 2520 and 2530. And any class that you're taking where you have to make pipe welds, it's very important that you consider the preparation and the fit up on these things. Your welding procedure specification considers your joint to be an essential variable, and the emphasis is on the word essential. And you want to make sure that your joint fit up and preparation is as accurate and consistent as you can make it from weld to weld, because it's going to make everything a whole lot easier for you. And if you get beyond certain limits specified in the welding procedure specification, then it's a failure before you ever get started. So let's look at page 21 out of your text. And your book states 4 different separate steps that you should take in preparing your pipe. First, you want to prepare the edges. Then you want to clean the joint surfaces. Then you want to fit up the pipes. And then you want to tack weld the pipes together. Now, this chapter is going to talk about each one of those in some detail. So let's drop down to the bottom of the page where it says preparing the pipe edges. Single V butt joints are usually used to weld sections of pipe together. Everybody's familiar with what a single V is, correct? What we've been using on plate, what we've been using on pipe. This is a single V. Its welding symbol is a V, like this. That's the welding symbol for a single V. And of course it can be with or without a land. Okay, the elements or parts of the joint have been given standard names, which are shown in figure 4.1. These names are used so frequently in pipe welding that they should be committed to memory. If you look at figure 4.1, it talks about your root opening, your bevel angle, which in industry, the typical bevel angle, unless it is otherwise specified, is 37.5 degrees. Many of them you'll run into will only be 30 degrees. So that's one bevel. Well, we got 2 bevels here. So we got 37.5 and 37.5 on each side. So the included angle, that is the 2 of them added together, is going to be 75 degrees. And that is called your included angle. You should memorize these. They will be on your test. Right here, what we call our land is properly called a root face. And that can be of varying sizes depending on the welding procedure specification and whether or not you're welding vertically up or vertically down. I believe that's all your book talks about on this one. Figure 4.2, they've given us some numbers. They've given us 37.5 and 75. Here they're saying 3/32 to 1/8 of an inch on your land. Of course, in pipe welding, if we're welding vertical up, we're teaching you to use a 1/8 inch root opening and a 3/32, pardon me, a 1/8 inch land and a 3/32 root opening. But again, as I say, that can vary. And your welding procedure specification gives you room to move around. Generally, on a welding specification, get that off of there. Your welding specification will say for your root opening, it'll say 3/32 of an inch plus or minus 1/16. And that really covers a lot of it. You can go up to 5/32 of a root opening if you want to. Or you can go down to 1/16 of a root opening if you want to. So that really gives you a lot of room to play with. But that is typically what you're going to see and what you can expect to run into. Okay. I'm reading from your book now. The bottom paragraph on page 22, it says, often the bevel cut is manually made using an ordinary hand oxygen cutting torch. This requires care and skill. When available, a pipe beveling machine is used as shown in figure 4.3. We have one of these pipe beveling machines. In fact, we have a couple of them in the welding lab. And if you'd like to learn how to use one of those, I'd be happy to show you. Hand-cut pipe beveling machines like this are used almost exclusively in the field. It's a saddle-type machine. You simply put it on top of the pipe, adjust your torch, and you work it back and forth and turn on your cutting air, and then you just slowly crank it around, and it will burn that pipe off, and it'll just fall off, and you'll have a nice smooth bevel on there. Of course, you're going to get some carburizing on the nipples, on the pipe nipples, from making that kind of a cut. They're going to carburize up, and you're going to want to take and clean that all off with a grinder. You're going to want to take and go around the inside with the grinder, or preferably a cobstone. And if one's not available, use a file and clean the mill scale and rust away from the inside. And then you're going to want to go around the outside also and clean this back at least a ½ an inch. And most recommendations are 1 inch, so you don't suck any of this mill scale or coating or paint or grease or anything else into the weld that can cause porosity. Let's see. Reading on the next page, it says, the surface produced by the oxyacetylene cutting torch will have a tightly adhering oxide film. If not removed, this film is very detrimental to the quality of the weld. For this reason, the beveled surface should be entirely free of the film before any welding is done over it. The oxyacetylene cutting torch also produces a rather rough surface that is difficult to weld over, so you want to make sure you smooth it out. If you're using a beveling machine, it's really not that bad. They really come out pretty nice. But if you have to hand bevel a piece of pipe, unless you're really good with a torch, it is pretty tough. And the one thing about hand beveling a piece of pipe that you need to bear in mind is that the cut that you make on the top of that pipe, if you've got that pipe like here, and you've made this cut, the most important thing to consider is how square is that face? How square did you keep that face? Because the face of that cut that you just made using a hand torch has got to fit up to another piece of pipe. And somebody's got to weld those two pieces of pipe together. So even more than having gouges and nicks in here, worry more about having the face of that pipe square. And if it's possible, get yourself you get a flat surface and lay it down and look, and you can see if it's not square or not. You'll be able to tell. If it's impossible to lay it down on a flat surface, say this is the butt end of a 15-foot piece of pipe, then get yourself a framing square and check it that way. And get it just as square as you could possibly make it, because that's probably, in my opinion, the most important thing. Okay, let's go back to your book. Cleaning the joint surfaces. Contaminants such as grease, oil, scale, or rust will have a harmful effect on the quality of the weld. As already explained, all traces of the oxide film produced by the oxyacetylene torch must be removed. The welder must also make certain that any other contaminants are removed before starting to weld. This can usually be accomplished by the vigorous application of a wire brush. Sometimes a wire brush won't get it. As I say, use a cobstone. If cobstone is not available, use a half-round file. Half-round files work real well for that. Fitting up the pipe. The two pipes to be welded together must be accurately aligned prior to welding. The inside surfaces of the pipes must blend together smoothly, as should the outside surfaces. In many instances, the pipes must be aligned so that the finished piping system will be in the correct location. Considerable skill is required to fit up two pipes in preparation for welding. This is an essential part of the pipe welder's craft. You've got to be able to fit your pipe up. Now individually, I'm sure Jeff and I have worked with each of you individually about how to get these things lined up. Most codes will allow you a 1/16 of an inch of misalignment on the inside. And not all pipe is going to be circular. It may be a little egg-shaped at times. So you want to get as accurate a fit up as you possibly can. And if you do have a little egg-shaped pipe, try to split the difference a little bit so that you don't exceed 1/16 of an inch of mismatch on the ID, the inside diameter of that pipe. There's ways to check your alignment, both for dogleg, what we call dogleg, and inside diameter dimensional alignment. And I think your book covers that a little more thoroughly later on. Let's look at, drop down a paragraph where it reads, short pipe nipples are not only used for practice welding, but also for jobs in the shop and in the field. The pipe nipples recommended for practice welding are 7 inches long. They are made from 8-inch Schedule 60 mild steel pipe, for which the actual outside diameter is 8.625 inches, or 8 5/8 inches. And the wall thickness is 0.406. We don't use that. The gentleman that wrote this book, at the time he wrote it, he worked for Hobart Institute of Welding in Troy, Ohio. And this is what he used in his program. In our program, in order to save material and still produce accurate, good quality welds, we use coupons that are 3 inches long, generally. Here's an example of them. They're 3 inches long, and we use 6-inch Schedule 40 and 6-inch Schedule 80. Well, this happens to be Schedule 40. So it has a wall thickness of a little over 1/4 of an inch. It's 2.80. 6-inch Schedule 80 has a wall thickness of 0.432. It's important to remember that when you take a welding test, usually under ASME, you're qualified for twice the thickness of the pipe that you actually weld. If you were to take an ASME test on this pipe, you would be qualified to weld 5/8 of an inch thick, almost 5/8 of an inch thick. If it was Schedule 80, you'd be qualified to weld over 3/4 of an inch thick. However, some codes will only allow you to weld to the actual thickness of the coupon that you took your test to. Depends on the welding test. Next page, page 25. It says to fit up the pipe nipples, first determine the required width of the root opening. Next, find a piece of wire having the diameter equal to the width of the root opening and bend it into a V shape. Well, this is what we use. This is 332 TIG wire. It's actually ER70S wire is its proper name. It's got a 70,000 pound tensile strength to it. And we just bend it into a V, and we'll lay it across like so onto the pipe. Let me draw this up on the board. It might be a little easier to follow me. When we're in the lab and I'm working with you one-on-one, looking down on your pipe like this, we're going to take a piece of wire and we're going to bend it, and that wire is going to look like this. When we're fitting these up and tacking them together, of course we're going to have another piece of pipe on top of this, and I'm going to ask you to put your first weld in on one of these sides, either here or over here. That first weld is just a tiny, tiny tack, maybe 1/4 of an inch long. Its only purpose is to tie the two coupons together. And as soon as you tie those two coupons together, you're going to reach over here on the other side and you're going to press down on it. So I've made my tack here, and I'm going to reach over here and I'm going to press down on that table and squeeze it down. The reason I'm doing that is to keep this from pulling up as that weld shrinks, as that little tack shrinks. Not only during that shrinkage process, not only will it pull up this way, but it can also shift side to side. So you want to check before you put any other tacks in. Reach down inside that pipe and fill the inside diameter again. Did it pull itself out of alignment? You want to double check that before you ever put that second tack in. Now when we put the second tack in, we're going to come directly opposite, and we're going to make a 1-inch tack right here. Bear in mind, the tack becomes part of the weld. So you want to have full penetration on there. Not only do you want to have full penetration, but when you get to the end of that tack, you want to poke that welding rod through to open up the keyhole. So it's looking like this when you're done. Here's your tack, and your bevel goes on like that. Here's where you started. But you've poked that welding rod through and you've opened up the keyhole. The reason we open up that keyhole is so that we can make a good tie-in to that tack when we come out. most of the problems I see in the welding lab is from people coming in and going out of these tacks. 80% of them, I would say, if they are having problems welding, they're having problems with these tacks right here. So make sure you poke that welding rod through there like that. Now once we've got that second tack on, then we're going to come between the legs of our gap rod and we're going to put another 1-inch tack on right there, just like that. Then we're going to remove this wire, and then we will put our final 1-inch tack on. Now when we go to weld this thing out, we'll start right here on that little 1/4-inch tack. We'll make this weld. Then we're going to come over here opposite. We're going to make this weld. Then, once this weld is completely in, we're going to go ahead and feather, and we'll remove that itty-bitty 1/4-inch tack that we put in at first. We're going to take it completely out, so it won't be there anymore. And then we'll make that weld, and then finally we'll make that weld. It's called quartering the pipe. We're going to quarter the pipe. We do this for a couple of reasons. It will balance the shrinkage forces in the pipe so that as it sucks up from the heat of welding, and this stuff is going to grow because we're dumping heat into it. That root opening is going to get narrower on us. By quartering the pipe, we're going to equalize that somewhat. And also, we're going to distribute the heat more evenly so that it doesn't get too hot and we blow through this pipe when we're welding in the 5G or the 6G positions. So we want to quarter the pipe because we're using just a small little piece of pipe here. If we were welding 20-foot lengths of pipe, that wouldn't be such a consideration. If you are welding 20-foot lengths of pipe, the thing to keep in mind is that you want to weld it so that the last part that you weld on that is the easiest part to get to. And then before you close it up, you're going to take a flashlight and you're going to look down in there and you're going to inspect your root pass from the outside. You're going to look down in there and make sure you don't have anything wrong with it. And then you'll put that last little 1/4 bit in there. That's the best way to check your root pass. Okay, let's go back to your textbook. I pretty much covered everything on that your book talks about. They talk about using a 3/4-inch tack. I like to use 1-inch tacks, but a 3/4-inch would work. And the way he's fitted up is slightly different from the way I've fitted up. Well, that's okay too. I would like you to follow the way that I've demonstrated here. Let's see. Okay, turning the page, your book says in the second paragraph, it says, in most cases, the ends of the tack weld should be ground to a feather edge to facilitate the tie into the root bead. That's very important. Let me show you again real quick. Here we've got one of our tacks. Well, if you look at it edge on from the top down, there's your pipe, and you're going to see a little bit of that tack in there like that and coming out like that. Well, that's all well and good. But it's really thick, and the heat of your welding rod is not going to burn through that thing unless you feather it down. So what you want to do is, let me draw a big picture here. Here's your tack, and here's your pipe going on like this. What you want to do is you want to take that grinder and you're going to grind it down just like that, and just like that. And you're going to remove most of that thickness. By removing most of that thickness, now you come down to a nice feather edge on each end. Then when you go to weld, you're going to strike your arc right here at the peak of that grind, right there. And then you're going to come out slowly. Just walk out real slow. And what I want you to keep in mind, and it's very important, is that burn through the tack before you reach the end of it. So if you can burn through that tack back up over here, then as you continue, you're going to have a smoothless transition into your weld. If you don't, if you come out too fast, and you don't burn through the end of that, you're going to have a skip. You're going to have a spot right there where your weld didn't tie into your tack. We call those toenails. And this right here is the biggest problem that people learning how to pipe weld have. So you want to make sure that you grind this properly and that you burn through the tack before you reach the end of it. Now before I get off this subject, there's one other thing I want to tell you. Here's your pipe, and here's your land. Okay, you got your 3/32 land all the way around there. Okay, And you've worked really hard to make sure that land is consistent and it's 3/32 all the way around. Then you put your tack in. Great. Well, and now you've gone and you've ground that tack just like I said, okay? You've got that little tiny peak in there, just like I've said. But you weren't careful. You ground past the end of the tack, and you got out there and you removed some of the thickness of that land. So instead of having a 3/32 land here at the end of your tack, you've only got a 32nd of an inch land. So there's no meat there to hold the heat. So when you come welding out of there with your stick, suddenly you hit that really thin spot of land, blow a big hole in it. So it's very important that whenever you prepare these tacks, whenever you grind them, do not grind past the end of the tack. Don't remove the meat of that land. You got to leave that in there to control the heat. Okay, let's see. What else do we have? Dropping down in the next paragraph, it reads, "It is important to start any weld correctly, whether tack welding or welding a longer bead. When the arc is struck, it should not be shortened immediately. Time should be allowed to stabilize the arc and allow the gaseous shield to form." And that's very important, especially in certification welding. Strike your arc, let it long arc just a little bit until you see it stabilized, especially if some of the flux has been removed or fallen off from around the tip of the electrode. Allow that the metal of the electrode to burn back until it is again surrounded by flux and the arc stabilizes, and then move into your short arc length. And when you're making these pipe welds, keep a short arc length. Keep it shoved in there just as tight as you can. Reading from the next page, it says, "For the tack weld, the correct procedure is to strike the arc ahead of the weld, or that part of the groove in which the weld is to be made, in which the tack weld is to be made, and then to maintain a long arc and move the electrode along the groove to the position where the weld bead is to start." So what they're telling us is, if I'm going to put a tack in here, draw another picture here. If I'm going to put my tack right here, I'm going to strike my arc over here. I'm going to allow it to stabilize as I'm coming back. When I get back, I'm going to shove that into a short arc and go ahead and deposit my tack. That way, if I have any arc strikes or any contaminants, it's going to burn out as I come back over it. So you're going to strike out in front, drop back, shorten your arc, put your tack in. Okay, the keyhole, page 27. The keyhole is an essential part in welding a root bead. It should be about 1 1/3 times the diameter of the electrode. The keyhole helps to ensure that the deposited bead will penetrate to the root, as evidenced by the small crown at the back of the bead. You should have about a 1/16 to a 1/8 crown, or inside reinforcement. They call it root reinforcement, on the inside of the pipe. That's the ideal. This crown should rise about 1/16 inch above the inside surface of the pipe. While welding, the welder should watch the keyhole constantly. You're always watching that keyhole. If the keyhole becomes enlarged, overpenetration will result. This can be corrected by reducing the welding current, or in some cases by increasing the welding speed. If the keyhole is too small, the penetration of the root bead will be insufficient. While slowing the speed of welding will help in some cases, usually it is necessary to increase the welding current to correct this condition. So when you strike your arc, and you're welding around here, and it doesn't matter what position you're in, you're welding around here, you're going to watch that keyhole. And you want to listen for that sound of penetration. If you're hearing that sound, you're probably getting through. In the 2G position, you want to be careful, because if you don't have enough of an up angle, you're not going to tie into this overhead pipe very well, and you're liable to get internal undercut on the up top side. So watch your rod angle, but we'll get into this more later when we get into the welding 2G position. Basically, watch that keyhole. If that keyhole starts to get too large, as he said, you can sometimes go ahead and increase your speed, but that may not always solve the problem. At that point, you might want to try using a whip. Just straight out and straight back. Don't try to chase the keyhole from side to side, because that's only going to enlarge the keyhole. But use the whipping motion out and back until it gets back to the size that you want. And then just go back to your drag technique again, like so. Now, if you're welding across here and it's getting too small, you're not sure you're hearing that sound, stop immediately. Stop immediately, clean off the inside, check, look, see if you're getting any penetration. If you're not, then you've got to go back and you're going to have to clean that up, grind it up. You may even have to remove some of the weld that you've already deposited and then increase your amperage and go back in again. Usually if you have lack of penetration, if that keyhole is too small, it's because you're either running too cold or you've got too thick of a land on it. That's why I say preparation of the joint is essential. Remember, we want that land to be 3/32 of an inch when we're welding in the vertical up position, and we want it to be not more than a 1/16 of an inch when we're welding vertically down. Okay. The whipping technique. Your book talks about using the whip technique, and in fact, the gentleman that wrote this book really likes the whip. I prefer to use the whip only when it's necessary to close the keyhole, but you can use a slight oscillation, which is something that I teach too. My preference is to simply strike the arc and just use a steady motion with it as you're going around the pipe, but sometimes you can just use that slight oscillation or a whipping technique to help control the electrode motion. And the center of this one paragraph on the whipping technique reads that the length of this movement should be short, about 1 1/2 electrode diameters, in order to maintain a gaseous shield over the molten metal at all times. So if you do decide that you've got to whip it, you're not going to go woo, woo. You're just going to go just small increments. Don't whip it very much. Basically, you want to whip it enough to clear the puddle and allow it to cool some, but not so far that you're going to lose your gaseous shield. Stopping the weld. The procedure that is used for laying down the root bead is continued until the bead is about 3/4 of an inch long. At this point, the weld is stopped. The procedure for stopping the weld is to push the electrode through the keyhole with a quick movement. As I've already described, we're just going to go right through the pipe. And it's poking. Don't be hesitant. Go boom, boom, just fast. Like you're punching a punching bag or something. Just shove it through there and then pull it back out again. And then we have a really, really nice picture of a keyhole on page 30. It's figure 411 in your textbook. And that is what our keyhole should look like when you're done. And then once you've got that done, you've got your 4 tacks in, you've feathered them, everything's right, then you're ready to make your weld. Okay, thank you much for your attention.